Thevenin's, really going to be Thevenin's theorem applied to something that has imaginary components for the actual impedance, okay? I'm just going to put this up here, and if you got one specific you want me to do, I'll be happy to do it, but I'll come up with one. Suppose we have this. Suppose we have a voltage here of, say, 10 at an angle of 0 degrees volts, and then I have a resistance here of 10 ohms, and then say I have an impedance here, right here of, say, minus J 10 ohms. That's a capacitor, right? And then I have an impedance here of, say, J 20. And then I have another resistance here of, say, 10 ohms. And what I want to do is find the voltage across here, plus to minus V out. But I want to use Thevenin's theorem. Can everybody hear me okay with this one? Now, several ways to do it. I mean, besides Thevenin, Noda would work very quickly with this one. But I'm going to go ahead and use Thevenin's for this. So first, I have to identify the load. RL here is 10 ohms. Does everybody agree with that? After you identify the load, you take it out. Can you all see in the back there? Okay, and hear me. If anybody, yes, sir. Okay, if you cannot hear me or cannot see or whatever, you got a problem, let me know, because it's hard for me to see because I'm looking over 5 or 6 people's heads. But if you can't, let me know. All right, does everybody agree that RL is 10 ohms and we can remove that? Can you all follow me, just assuming in your mind it's gone? Okay, matter of fact, let's do this to try to make it more gone. All right, so there's nothing there. Now, the next thing I have to find is the open circuit voltage, right? Before I calculate that, I'm going to make a comment or question. Don't answer, just think about this. If that's removed, how much current is going through that impedance? 20 ohms. Don't answer, just think about it. Now, how many know? It should be everybody. How much? 0, right? Because there's no way for current to flow through there. I've removed the load. That's important. All right. So now I want the open circuit voltage. If no current's flowing there, do you all see that the open circuit voltage is the voltage across that capacitor? How many see that? Can you see it in the back or not? Far back. You understand what I'm saying? I mean, you with me at that? If there's no current through here, then literally this voltage is this voltage, right? There's no voltage drop across the inductor. All right, how do we get that? If we want this voltage right here, now take a look. Isn't that just voltage division between these two elements times 10? If we have 10 volts at 0 degrees and we use voltage division here, how many see we'll get the voltage across the capacitor? That will be the open circuit voltage. Show of hands here. Agreed? I mean, so there's not a whole lot of hands, not everybody's going up. Does anybody not see it? I'm assuming you do, and please just understand, I have to ask these questions to try to figure out if you're understanding what I'm doing. All right, that means to get this voltage, the easiest way for me would be voltage division. Do you agree with that? All right, so for voltage division, I take the source voltage, which I put at 0 degrees, but if it had an angle, you'd have to include it. It's just 10, right? Then I'd multiply by minus J10, right? And I'd divide by 10 plus J10. Do you all agree with me? Everybody? Now I'm going to do something here, and I'm trying to make sure you understand the reason for it. I try to simplify things. When I look at something, before I move on, I see if I can simplify. When I take a look at here, I have 10 and 10, top and bottom. If I divide both top and bottom by 10, I get 1, right? And then I get 1 plus J1. So this can be reduced to 10 over minus J over 1 plus J. Do you all agree with what I've done there? Okay, are you with me? If it seems too simple, just go along with me because I'm trying to show you how simple most of this stuff actually is. All right, now the next thing I'm going to do, and I'm going to do this without a calculator. I can see I got 1 plus J. I know that that is 1 and J, which means the hypotenuse here is square root of 2, and the angle is 45 degrees. I can do that in my head, and probably you can too, especially if you're Emmys. And I know minus J is really 1 at an angle of minus 90. Do you follow me now? Y'all hear me back there, guys? All right, so now I can say that this is equal to 10, and this is simply 1 at an angle of minus 90 degrees, and this is square root of 2 at an angle of 45 degrees. Now, does everybody see that? This is how professors do this. We don't usually use a calculator unless it's absolutely necessary. So if I take a look at this, I know that I have 10 over the square root of 2, right? And that's what, 7.07 something, right, isn't it? You can go ahead and carry it out, but you with me? How many are with me so far? I've got 10, I got the square root of 2. That's the only magnitudes I have to worry about, correct? What about the angles? Anybody now, somebody else besides me, and you can shout through your math. If I have minus 90 divided by 45 like that, what do I do with that 45? Anybody? It's really going to be minus 90 minus 45, isn't it, class? So minus 135. Are you with me? So that's minus 135. Now, I can add 360 degrees to that and get a positive angle, but it's just more information than I need. This is an acceptable answer. Are you with me? That is the answer for the open circuit voltage. Now, the next thing you need for Thevenin is what? Anyone, you can whisper it or mumble it or anything. R Thevenin or Z Thevenin? I mean, it's a Thevenin equivalent impedance, actually, right? So what is Z Thevenin for this one? Well, when I come back to the problem that I created, what do I have to do, essentially, to get that? I'm looking through these terminals and trying to get the actual impedance seen by the load, right? There's one essential thing I do. Anyone? One very critical thing I do before I do any calculations at all. Say it. You know it. I shut off the sources, right? Voltage sources become short circuits. Current sources become open. I didn't put a current source in there, forgive me. Current sources you rip out, voltage sources you short. So if and I'm going to just do it right here if you don't mind. If I short this, right, and I want the impedance, can everybody see it's going to be J20s in series, right? And then can you see the 10 and the minus J10 are in parallel? Show of hands if you can, right? So that means it's going to be plus, and it's really going to be 10 in parallel with minus J10. Now, I'm going to leave it like that for a reason, because I can go through that calculation if you want me to, but it's not really necessary to show what I'm doing. If you want me to, I'll do it. Are you with me on that? You just got to calculate the parallel combination. And if you do this, it's minus J10 times 10, which is minus J100 over 10 minus J10. It's multiply the two, then add them. So I could put that down here. So it's minus J10 times 10 over 10 minus J10, or minus J10 over 1 minus J. So this is really going to be 10 over 1 minus J. Now, I've done a ton of these things, so it's a little more apparent to me than some of you that have not worked in this area. I'm not the brightest or the best, but I do know if you do enough of these things, it's second nature. I promise you it is. It's not hard. So that's plus J20. Now what do I do? Someone, not you, someone else. How about from the far back corner with the black mask in the very back corner? Can you hear me okay? What do I do next? Circuit, right? Going to assemble it. All right, so my assembly starts with the open circuit voltage. That's this, 7.07, or really what, 10 over the square root of 2 if you want. And it's going to be that at an angle of minus 135, right? At minus 135 degrees. And then what? After that, I put the series Thevenin impedance, right, which is this. And do you mind if I just leave it as Z Thevenin here? Because I think this part is just too much information. And then what do? I replace the load, right? Now I put the load back in that I've taken out. Correct, class? That load was 10. And now I wanted the voltage, right? So how do I go about getting that voltage? And I'm going to leave it in terms of Z Thevenin, because what do you know happens here? I'm going to just talk my way through this 10 over 1 minus J10. Hear me now, and don't freak out, all right? If I have 10 over 1 minus J10, That's the same thing as 10 over the square root of 2, right? At an angle of minus 45 degrees, isn't it? Right? Magnitude is 1, angle is minus 45 degrees, right? Now, if I take the minus 45 degrees upstairs, it becomes plus 45. And then I have to add that to J20. If you want to do it with polar numbers, this would be 20 at an angle of 90 degrees, right? You'll be with me? J, just J is 1 at an angle of 90. 20J is 20 at an angle of 90. And then you would add these two. I'm not going to bother with that. That's wasting too much time on something that's just really bookkeeping. Finally, for V out, what would it be? It would be the load impedance or resistance of 10, right, over Z Thevenin. I hope this answers your question. Plus 10 times 7 point. Pardon me? Oh, thank you. Yell at me if you, it should be. Times 7.07 at an angle of minus 135 degrees. Now, I can tell you right now, this right here is going to be a little more work than I bargained for. I can, what I would do normally, if this is just me and a piece of paper, I would go ahead and take the complex conjugate of this thing and multiply top and bottom, get it into a real and imaginary parts and add them to this part. Then I get the polar form. But don't worry about this. Your calculators do this quickly and seamlessly, okay? How many understand what I said and why I said it now about this one? Is there another question? Because I think we're going to just have to figure. Yes, far back. This voltage, which one? R Thevenin doesn't have a voltage division. You mean VOC? R Thevenin is just, it's an impedance, not a voltage division. Just tell me where to stop. This? That's Z Thevenin. There's no voltage division here. Are you okay? What? Say that again, sir. Oh, the voltage division here? Here's what I'm doing. I'm saying if I, what? Oh yeah, thank you. If you want the voltage here, it would be, I take this value, whatever it is, the load impedance, and then I divide it by this plus this, because there's only two elements. Is that what you're talking about? What are you talking about? Oh, okay. This, you're talking about this right here? That's not voltage division. I took 10 in parallel with minus J10. Okay, here's what I'm doing. If I have 10, they're talking about 10 in parallel with minus J10 because this is shorted, right? So that's literally here, okay? With me? All right, if they're in parallel, well, you can take 1 over 10 plus 1 over minus J, or if you multiply top and bottom by the first and the second, you're left with 10 times minus J10 over 10 plus, or 10 minus J10. How many see that right there? 2 in parallel would be first times the second over the first plus the second, right? All right, now if I do that, what I'm saying is if I divide top and bottom by 10, I get minus J over 1 minus J. Okay? That's all I'm doing. Are you okay with it? I can't. What? What kind of calculator? It's a little late in the game, but anybody give them a piece of advice with it that has an 84 and knows what they're doing? This shouldn't be, it should be seamless. I promise you, if you've looked at the videos, did you put them up or who put them up? Whoever put the videos up, I appreciate it. You put them up, somebody put another thing for it, some other calculator, I think. Anyway, yes, sir.
For the DOC, why is it 10 plus J10 on the denominator?
All right, when we're getting the open circuit voltage, right? All right, hold on. Were you saying 10 plus J10?
10 times bigger J10 over 10 plus J10. Would it be 10 minus J10?
Where are you looking here? I'm not. This is VOC, right? All right, if I want the open circuit voltage, I take the source voltage, right? And then it's divided by, forget this part of the circuit, it's divided by these two, right? So then I take minus J10 and divide it by minus J10 plus 10, right? Oh, minus J10, you are so right. That's my bad. A minus J right there. So right there, right? Make that minus 45, correct? And that makes this top one, that's going to be minus 45, right? What? Yeah. I'm sorry. But you follow what I'm doing, though? The technique, that's a sign. This should be a minus 45. It's going to change that and make this minus 45 because it'll change signs. And then down, the magnitude is going to be the same. And then, let's see. That's right. So this is just going to be 7.07 at an angle of minus 45. My bad. Thank you very much for calling me out on that. I appreciate it. He's right. All right, other questions? Because we're about. All right, can I show you where we're going? And now, y'all realize we didn't use one Laplace transform to solve one differential equation. You should be grateful for that. In the course I teach in electrical and computer engineering, any of the courses, we write differential equations and solve them. The sources aren't simple. They're more complicated. How many have had differential equations in Laplace transform solutions? Okay, you grateful now? Because I don't get tables. All right, I promise you I don't. All right, what you're going to do now is transient solutions. We're going to just mention this. If you don't want to write it down, you don't have to, but I want to just get you at least geared up for where we're going. A transient solution is like this. We have something called a switch that closes as usually t equals 0, and it's connected to a battery of some sort, plus the minus the voltage V naught. Here, when I say transients, it means usually this. I have some element, some resistive element that will slow the rate that the actual event occurs. In this case, it's going to be a charging of a capacitor. And then I'm going to have some device that stores energy, in this case, a capacitor. And I'm going to want to know what the voltage is as a function of time across that capacitor. Now, without saying anything more about this, I can write a differential equation and solve this. I promise you I can. And you have done this back in the day when you took differential equations. This switch right here was normally done with a U of t function, or I guess they call it a switching function, U of t. How many remember U of t function, switching function, something that's 0 for t less than 0 and 1 for t greater than 0? How many remember that? Transitions, it's called a switching function, U of t, step function, I don't remember all the names for it, but it's something that just mathematically describes a state from a 0 to a 1 at a transitioning point. Now, I can write that. I can write an equation for the voltage drop here as I times R, I of t times R, and the voltage drop here, right? Well, I know that the voltage drop here, if that's just a voltage V across a capacitor, then the current through the capacitor is C dV dt, right? And therefore, instead of just putting I of t here, I can put C dV dt for I times R plus V of t would be equal to this voltage. Now, you don't need to write this down, but what I'm trying to do is show you where we're going. And the solution to this will have an exponential increase from 0 to some value. That's what we're going, and it's in chapter 3. I'm going to be going through, it's going to be in chapter, I don't know, 4 or 5 in your book, but I'm going to go through that. That's the one that Roppel and Gross wrote. I'm going to go through this my way. I hope you appreciate it. I don't mind these guys in their book, but it's very thin as far as the details on a lot of stuff. That's the reason I use my own notes set. And now, even though this is a short quiz, take everything off your desks. No wearable electronics, no anything else, and thank you. And I apologize for not having enough desks in here, and I don't know why they didn't open that side. Yeah, give me half. I'll start at that end.